For decades, America's rail yards depended on small locomotives with big jobs, sorting cars, building trains, feeding industries, keeping the entire system alive. These weren't the glamorous machines pulling transcontinental freights or racing passenger trains across the country. They were the workhorses that made everything else possible, laboring in yards and industrial sidings, often unnoticed but absolutely essential. And in 1974, EMD introduced a machine that would become the final chapter of a dynasty, the MP15. It was tough, compact, and engineered to survive in the harshest industrial environments. It could work a classification yard all day, then head out on a local freight run. It could couple and shove cuts of cars with precision, then run in multiple unit with road locomotives when needed. It was the last great American switcher, and it proved that sometimes the most important locomotives aren't the biggest or most powerful, but the ones that show up every day and do the work nobody else wants to do. This is the story of the EMD MP15 switcher family, a line of locomotives that represented the culmination of decades of switcher development and became the standard by which all industrial locomotives would be measured. By the early 1970s, EMD's switcher lineup was showing its age. The SW series, SW1, SW7, SW9, SW1200, and SW1500 had served the railroad industry well for decades. These compact locomotives, typically producing between 600 and 1,500 horsepower, were the backbone of yard operations across North America. They sorted cars in classification yards, moved cuts between tracks, built outbound trains, and handled the constant shuffling that kept freight moving. But the railroad industry was changing, and the demands on switchers were evolving in ways that exposed the limitations of the older designs. The growth of intermodal traffic was transforming rail operations. Container trains were becoming longer and more frequent, which meant yards had to process more cars more quickly. The old switchers, designed in the 1940s and 1950s for a different era of railroading, were adequate but not ideal for this increased workload. They lacked the speed and flexibility that modern operations demanded. Industrial rail service was expanding dramatically. Steel mills, refineries, chemical plants, automotive facilities, and ports all depended on rail service to move raw materials and finished products. These industries often operated their own locomotives or contracted with railroads for dedicated switching service. The locomotives serving these customers needed to be reliable above all else. A breakdown in an industrial setting could shut down an entire production line, costing thousands of dollars per hour. The older SW series switchers were dependable, but they were also becoming harder to maintain as parts supplies dwindled and the locomotives themselves accumulated wear from decades of hard service. The technical limitations of the traditional switcher design were becoming apparent. Most SW series locomotives rode on AR Type A switcher trucks, simple, robust designs that worked well at the low speeds typical of yard work, but provided a harsh ride and limited capability at higher speeds. This made them unsuitable for road work, even on light branch lines or local freights. If a railroad needed a locomotive for both switching and occasional road service, they had to assign a larger, more expensive road switcher, like a GP38, which was often overkill for simple yard work. Multiple unit operation was another issue. The older switchers generally lacked the MU connections and control systems that would allow them to operate and consist with road locomotives. This limited their flexibility. A switcher that could only work alone in a yard was less valuable than one that could also head out on a transfer run or local freight, coupled to other locomotives as needed. Electrical systems on the older switchers were also becoming outdated. The control systems were based on technology from the 1940s and 1950s, reliable enough, but not as efficient or easy to troubleshoot as the newer modular systems EMD had developed for their road locomotives. Maintenance forces were becoming familiar with the -2 electrical systems used in locomotives like the GP38-2 and SD40-2, and they wanted switchers with similar technology for consistency across the fleet. The physical environment in which switchers worked was also demanding. Rail yards are brutal places for locomotives. Constant starting and stopping puts tremendous stress on mechanical and electrical systems. Dust, dirt, and industrial pollutants clog air filters and radiators. In ports, salt air corrodes electrical connections. In steel mills and refineries, extreme heat and chemical exposure take their toll. The older switchers handled these conditions reasonably well, but there was room for improvement in cooling system design, air filtration, and component protection. Railroads were also looking ahead to the future of yard operations. Hump yards, facilities where cars were pushed over a hump and allowed to roll down into classification tracks by gravity, were becoming more sophisticated. These operations required locomotives with precise speed control and excellent low-speed torque characteristics. The older DC generator systems worked, but newer technology offered better performance in these demanding applications. By the early 1970s, it was clear that the railroad industry needed a new generation of switchers. They needed locomotives that could handle traditional yard work, but also had the capability to work on the road when needed. They needed modern electrical systems that would be easy to maintain and diagnose. They needed better cooling systems to handle harsh industrial environments. They needed trucks that could provide a smooth ride at higher speeds. And they needed all of this in a compact package that could still navigate the tight clearances and sharp curves of industrial trackage. EMD recognized this need and began designing a switcher that would address all these requirements. They wouldn't start from scratch. EMD's approach had always been evolutionary rather than revolutionary, but they would take the best of the EMD1500 and improve it substantially. The result would be a locomotive that represented the final evolution of the traditional American switcher, incorporating lessons learned from decades of experience and equipped with technology that would keep it relevant for decades to come. The market was ready. Industries were expanding. Yards were getting busier. Older switchers were wearing out. What railroads needed was a machine that could do everything a traditional switcher could do, plus handle light road work, plus operate in multiple unit with modern road locomotives, plus survive in the toughest industrial environments. They needed a multi-purpose locomotive that was still compact enough for yard work. They needed the MP15. In 1974, EMD introduced a switcher unlike any that had come before it. They called it the MP15, a designation that stood for Multi-Purpose 1500 Horsepower. That name was deliberate and revealing. This wasn't just another switcher. It was a hybrid machine designed to bridge the gap between pure switching locomotives and light road power, combining the compact size and maneuverability of a yard engine with capabilities that extended far beyond traditional switcher roles. The MP15DC, as the first variant was designated, was based on the SD1500 but represented a substantial redesign rather than a simple update. EMD took the best aspects of the SD1500, its reliable 12-cylinder 645 engine, compact dimensions, and proven mechanical systems, and reimagined them for a new era of railroading. The result was a locomotive that looked similar to previous switchers but was fundamentally more capable. At the heart of the MP15DC was EMD's 12-645E diesel engine, the same engine family that powered the successful GP38 and was used in various forms across EMD's product line. This was a two-stroke diesel engine with 12 cylinders in a V configuration, each cylinder displacing 645 cubic inches. At 900 revolutions per minute, it produced 1,500 horsepower, adequate for all traditional switching duties and enough for light road work as well. The choice of the 645E engine was strategic. This was mature, proven technology with an established track record of reliability. Parts were readily available. Mechanics across North America understood this engine. It could run for years with proper maintenance and could be overhauled when necessary, without exotic tools or specialized knowledge. The frame of the MP15DC was longer than traditional switchers, a critical design decision that enabled several important capabilities. The extended frame length allowed EMD to offer two different truck options, giving railroads the flexibility to choose the configuration that best suited their needs. For pure yard work, the MP15DC could be equipped with AAR Type A switcher trucks, the traditional design that provided excellent low-speed traction and tight radius curve capability. But for railroads that wanted more versatility, EMD offered Blomberg B trucks, the same design used on road locomotives like the GP38. This truck option was transformative. Blomberg B trucks provided a dramatically better ride quality than switcher trucks, using a more sophisticated suspension system with better damping characteristics. They allowed higher sustained speeds without the harsh jarring motion that made switcher trucks uncomfortable at anything above 20 miles per hour. With Blomberg trucks, the MP15DC could comfortably operate at 40 or 50 miles per hour, making it suitable for local freight runs, transfer moves between yards, and branch line service. A locomotive that could switch cars all morning and then head out on a local freight in the afternoon was far more valuable than one limited to yard work. The hood layout on the MP15 was redesigned for improved cooling and maintenance access. The cooling system was a critical consideration for a locomotive designed to work in industrial environments. Switchers often operate in confined spaces where ventilation is poor. They work in dusty conditions where air filters clog quickly. They run continuously at varying loads, from idling between switching moves to full throttle when shoving heavy cuts up yard leads. The cooling system had to handle all of this reliably. EMD equipped the MP15DC with a high-capacity radiator section at the rear of the locomotive, with large radiator screens designed to resist clogging from industrial dirt and dust. The cooling fans were sized to move large volumes of air, even in hot weather or confined spaces. The entire cooling system was designed with maintenance in mind. Screens could be removed and cleaned quickly, and the radiator core was accessible for periodic flushing to remove accumulated debris. This attention to the realities of industrial service would prove crucial to the MP15's reputation for reliability. The electrical system on the MP15DC was straightforward and robust. An AR-10 alternator, driven by the diesel engine, produced electrical power that was rectified to DC and fed to the traction motors. This was simple, proven technology that provided excellent low-speed torque characteristics, exactly what was needed for switching service. The control system was based on EMD's contemporary road locomotives, using modular components that were easy to diagnose and repair. This gave maintenance forces the advantage of working with familiar technology across both switchers and road power. One of the most significant features of the MP15DC was its full multiple-unit capability. Previous switchers often had limited or no MU connections, which restricted them to solo operation. The MP15DC could be operated in multiple unit, consists with other MP15s or with road locomotives like GP38s, GP40s, or SD42s. The control systems were compatible, the electrical connections were standard, and the operating characteristics were predictable. This meant an MP15DC could be dispatched on a local freight run, coupled to a GP38, with both locomotives under the control of a single engineer, or several MP15s could work together on heavy switching moves. This flexibility dramatically increased the utility of the locomotive. The cab design reflected EMD's extensive experience with switcher operations. Visibility was paramount in yard work, where engineers needed to see ground personnel, switches, signals, and other equipment. The cab featured large windows providing excellent sightlines in all directions. The control stand used EMD's classic desktop layout, with the throttle, reverser, and brake controls positioned for easy reach. The gauges and indicators were logically arranged and easy to read. Everything about the cab was designed for long days of repetitive switching moves, where fatigue could lead to mistakes and mistakes could lead to accidents. The MP15DC's weight distribution was carefully calculated. At approximately 120,000 pounds, it was heavy enough to provide good traction without being so heavy that it was restricted from light rail branch lines or industrial sidings. The weight was distributed across the trucks to maximize adhesion while maintaining acceptable axle loadings for most trackage. This balance was critical, too light, and the locomotive would slip its wheels constantly, too heavy, and it wouldn't be able to go where it needed to work. EMD's marketing for the MP15DC emphasized its versatility. This was a locomotive that could replace aging SW series switchers in yards, but it could also handle assignments that previously required larger, more expensive road switchers. For railroads looking to standardize and simplify their fleets, the MP15DC offered compelling economics. One locomotive type that could handle multiple roles meant fewer spare parts to stock, simpler crew training, and more flexible locomotive assignments. Initial orders came from railroads across North America. Class 1 carriers like Southern Pacific, Union Pacific, Burlington Northern, and Conrail bought MP15DCs for yard and industrial service. Smaller railroads ordered them for use as their primary road power on light branch lines. Industrial operators, steel companies, refineries, ports purchased them for plant switching. The variety of customers demonstrated the broad appeal of the multi-purpose concept. The MP15 DC represented the culmination of EMD's switcher development experience, incorporating lessons learned from 30 years of building yard locomotives. It wasn't revolutionary in the sense of introducing radical new technology. It was revolutionary in the sense of getting everything right: the power level, the truck options, the electrical systems, the cooling capacity, the MU capability. Every detail reflected practical experience and careful engineering. This was a locomotive designed by people who understood how switchers actually worked and what problems they actually encountered. The success of the MP15 DC proved that there was still a market for well-designed switchers in the 1970s. Despite predictions that yard automation and larger road locomotives would eliminate the need for dedicated switching power, the reality was that yards still needed compact, maneuverable locomotives with excellent visibility and precise control. The MP15 DC filled that need perfectly, and it did so with capabilities that extended far beyond traditional switcher roles. It was the switcher reimagined for a new era, and it would set the standard for industrial locomotive design for decades to come. What made the MP15 family so successful wasn't just power or versatility. It was engineering discipline applied to every system, every component, every detail. EMD had been building locomotives for decades, and all that accumulated knowledge went into creating a machine that was reliable, simple to maintain, and flexible enough to handle whatever work came its way. Understanding the MP15 requires understanding the engineering that made it exceptional. The prime mover, the diesel engine that powered everything else, was the 645E, and it was the foundation of the MP15's reliability. This was the same engine family that powered thousands of GP38s and was used throughout EMD's product line in various configurations. The 645 designation came from the displacement per cylinder, 645 cubic inches. With 12 cylinders arranged in a 45-degree V, the total displacement was 7,140 cubic inches, or about 127 liters. This wasn't a particularly exotic engine. It was straightforward, robust, and well understood. The 645E was a two-stroke diesel, which gave it characteristics that were ideal for locomotive service. Two-stroke engines fire every revolution rather than every other revolution like four-stroke engines, which provide smoother power delivery and better low-speed torque. The engine used EMD's root blower system, a mechanically driven air pump that scavenged exhaust gases and forced fresh air into the cylinders. This allowed the engine to breathe effectively even at low speeds, providing strong pulling power from a standstill. The modular design of the 645 engine was one of its greatest advantages. Each cylinder was a complete power assembly that could be removed and replaced individually. If one cylinder developed problems, you didn't need to tear down the entire engine. You could pull that one power assembly, inspect it, repair or replace components, and reinstall it. A well-equipped shop could swap out a power assembly in a few hours. This modularity extended throughout the engine. Fuel injectors, exhaust valves, connecting rods, all were designed for individual service rather than requiring complete engine overhauls. Maintenance. Intervals on the 645V were generous. With proper care, regular oil changes, fuel filter replacement, cooling system maintenance, these engines could run for years between major overhauls. When overhauls were necessary, they were straightforward. Rebuild kits were available with all necessary components. Procedures were well documented. Any diesel mechanic with locomotive experience could perform the work. This maintainability was critical for customers operating the MP15 in industrial settings, where specialized locomotive repair facilities might not be available. The electrical system on the MP15 DC was deceptively simple but highly effective. The AR-10 alternator, driven directly by the diesel engine, generated three-phase AC electrical power. This AC power was then rectified, converted to DC, by a bank of silicon diodes. The DC power flowed to the traction motors through contactors and resistors that controlled the voltage and current. This gave the engineer precise control over locomotive speed and pulling force. The DC traction motors themselves were rugged, proven designs. Each motor was mounted on the truck, directly coupled to one axle through gear reduction. The motors were series-wound DC machines, which gave them excellent torque characteristics at low speeds, exactly what was needed for switching service. When starting a heavy cut of cars from a standstill, these motors could produce tremendous pulling force. As speed increased, the torques naturally decreased, but this matched the requirements of most switching operations perfectly. The control system allowed the engineer to adjust the power delivered to the motors through a notched throttle. 8 throttle notches provided graduated power levels from idle to full power. In each notch, the control system would adjust the field strength of the traction motors and the resistance in the circuit to maintain optimal performance. The system was entirely automatic once the engineer selected a throttle position. No manual transition between series and parallel motor configurations. No complicated procedures to remember. Just set the throttle and the locomotive would respond predictably. The cooling system was oversized for good reason. Switchers work hard in difficult conditions. They might idle for extended periods, then immediately go to full throttle. They operate in confined spaces where ambient temperatures can be high and air circulation poor. They work in dusty environments where radiator screens can clog. The MP15's cooling system was designed to handle all of this without overheating. Large radiator sections at the rear of the locomotive provided ample heat rejection capacity. The radiator core was substantial, with enough surface area to cool the engine even in hot weather at sustained full throttle. 2 large cooling fans, driven by electric motors, pulled air through the radiators. These fans were thermostatically controlled, automatically adjusting their speed based on coolant temperature. The system could move enormous volumes of air when needed, ensuring the engine stayed within safe operating temperatures. The radiator screens deserve special attention in the design. In industrial environments, steel mills, grain elevators, ports, airborne debris is constant. Paper, dust, chaff, metal particles, all of this can clog radiator screens and reduce cooling efficiency. The MP15 screens were designed to be quickly removable for cleaning. Maintenance crews could pull the screens, blast them clean with compressed air, or wash them, and reinstall them in minutes. This simple design feature prevented many potential overheating problems. The air intake system included robust filtration to protect the engine from ingesting damaging particles. Large air filter boxes housed replaceable filter elements that trapped dust and debris before air entered the engine. Regular filter changes were part of routine maintenance, and the filters were sized to provide long service intervals, even in dusty conditions. Clean intake air was critical to engine longevity. And EMD ensured the MP15 had adequate filtration for the harsh environments where it would work. The control stand and cab layout reflected decades of experience with what engineers actually needed. The desktop-style control stand placed all critical controls within easy reach. The throttle, a notched lever that moved through 8 power positions, was positioned for comfortable operation with the right hand. The reverser, controlling whether the locomotive moved forward or backward, was a large lever that could be easily seen and felt, critical for preventing directional errors during switching. The independent brake and automatic brake controls were logically positioned and clearly labeled. Gauges provided essential information: engine speed, main reservoir air pressure, brake line pressure, cooling water temperature, and oil pressure. These weren't digital displays with multiple screens and menus. They were simple analog gauges that showed critical information at a glance. An experienced engineer could scan the gauges in seconds and know immediately if something was wrong. The simplicity of the analog instruments meant fewer electronic failures and easier troubleshooting when problems did occur. Visibility from the cab was excellent in all directions. Large windows at the front, sides, and rear allowed the engineer to see ground personnel, switches, and other equipment. The cab was positioned to provide good sightlines down both sides of the locomotive, essential for switching operations where the engineer needed to watch cars being coupled or spot specific locations along a track. Some MP15s were equipped with enlarged rear windows or additional mirrors to improve visibility when running in reverse, common during switching moves. The multiple unit capability that EMD built into the MP15 was more sophisticated than it might seem. MU connections weren't just electrical jumpers that allowed multiple locomotives to operate together. They required compatible control systems, matching throttle response characteristics, and coordinated dynamic braking. The MP15's control system was designed to interface seamlessly with EMD's road locomotives, So an MP15 and a GP38 could run together with identical performance from each unit. The MU receptacles were standardized across EMD's product line, with 27-pin connectors that carried all necessary control signals. When multiple locomotives were coupled together, connecting the MU cables linked their control systems. The lead locomotive, the one with the operating crew, would send commands through the MU cables to the trailing units. All locomotives would respond to throttle changes simultaneously. All would transition between power settings together. All would apply dynamic braking together, if so equipped. This coordination was essential for smooth operation and prevented the lurching and slack action that could occur if locomotives weren't perfectly synchronized. The Blomberg B trucks, when specified, were the same proven design used on thousands of GP series locomotives. These trucks used a three-piece design with coil spring suspension that provided excellent ride quality. The truck frame was a heavy steel casting designed to handle the stresses of starting and stopping heavy trains. The suspension system allowed vertical motion to absorb track irregularities while providing lateral stability for safe operation at speed. The axles were connected through equalization systems that helped maintain even weight distribution across all wheels, improving traction. The traction motors mounted to the Blomberg trucks were nose suspended, mounted directly to the truck frame with one end supported by the axle through the gear case. This design was simple and robust, capable of handling continuous high torque loads without failure. The gear reduction ratio was selected to provide a balance between starting tractive effort and maximum speed. The MP15 wasn't designed for high-speed operation, but with Blomberg trucks, it could comfortably sustain 40 to 50 miles per hour on branch lines or light road work. Brake systems on the MP15 included both air brakes and, on some units, dynamic braking. The air brake system used standard Westinghouse 26L equipment, the same system used throughout the North American freight car fleet. This ensured compatibility and meant that engineers trained on any North American railroad could operate an MP15 without special instruction. The automatic brake controlled the entire train's brakes through the brake pipe. The independent brake controlled only the locomotive's brakes, useful for controlling speed during switching moves without affecting coupled cars. Dynamic braking, when equipped, used the traction motors as generators to slow the locomotive. When the engineer moved the dynamic brake lever, the traction motor's electrical connections were reconfigured so they generated electricity rather than consumed it. This electrical energy was dissipated as heat through resistor grids, typically mounted on the roof of the locomotive. Cooling fans pulled air across these resistors to prevent overheating. Dynamic brakes were particularly useful in hump yard operations, where precise speed control was critical, and in industrial settings with steep grades where continuous air brake use could lead to brake heating. Every system on the MP15 reflected practical engineering decisions based on real operational experience. Nothing was oversized unnecessarily, but nothing was undersized either. The locomotive had exactly the capability it needed to do its job reliably, year after year. This balance, adequate power, robust components, maintainable systems, thoughtful design, was what made the MP15 family so successful. EMD had built a switcher that would simply work in any environment, doing whatever was asked of it. That was the engineering achievement that mattered most. The MP15 family wasn't just one locomotive. It was a platform that EMD adapted to serve different markets and different operational requirements. Each variant represented a specific engineering solution to particular challenges, and understanding these differences reveals how EMD thought about locomotive design and how railroads used these machines. The MP15DC, the foundation. The MP15DC, introduced in 1974, was the base model and the most straightforward member of the family. Everything we've discussed so far, the 12-645E engine, the DC traction motors, the optional Blomberg B trucks, the multiple unit capability, defined the MP15DC. This was the locomotive designed for traditional switching service with the added capability of light road work. In practice, the MP15DC found homes across an incredibly diverse range of operations. Major railroads used them in classification yards, where they sorted incoming cars and assembled outbound trains. These were busy, demanding assignments requiring constant movement. An MP15DC might spend an entire shift shuttling between tracks, coupling and uncoupling cars, shoving cuts over humps, pulling strings out of classification tracks. The locomotive would be in near constant motion, throttle constantly changing, reverser frequently shifted. This was exactly the kind of work the MP15DC was designed for, and it excelled at it. Port operations became a major application for MP15DCs. Container ports, particularly on the West Coast, needed locomotives that could maneuver in tight spaces between stacks of containers while having enough power to move long cuts of heavy container cars. The MP15DC's compact size allowed it to work in confined port facilities, while its 1,500 horsepower provided adequate power for the loads it would handle. Several ports purchased their own MP15DCs for dedicated service, operating them continuously to keep cargo moving between ships and trains. Industrial switching was another natural fit. Steel mills used MP15DCs to move raw materials to blast furnaces and finished products to shipping docks. Refineries and chemical plants used them to spot tank cars at loading racks. Automotive plants used them to handle boxcars full of parts and finished vehicles. Paper mills, grain elevators, coal-fired power plants. Any industry with significant rail service could benefit from having a dedicated switcher, and the MP15DC proved ideal for this work. Its reliability was particularly important in industrial settings where a locomotive breakdown could disrupt an entire production process. Some railroads used MP15DCs equipped with Blomberg trucks as power for local freight trains and branch line service. These assignments took the locomotive out of the yard and onto the main line, where it would pull a short train of cars serving industries along a branch line. The locomotive might make several stops, switching cars at each customer, before returning to the yard. This kind of work required the smooth ride and higher speed capability that Blomberg trucks provided, and the MP15DC handled it comfortably. For lightly trafficked branch lines, a single MP15DC was often perfectly adequate power. Transfer runs between yards were another common MP15DC assignment. In large metropolitan areas, railroads often operated multiple yards serving different functions or different parts of the city. Cars needed to be moved between these yards, and a transfer run, typically just a locomotive and a string of cars running from one yard to another, was how it was done. The MP15DC could make these moves efficiently, and with MU capability, 2 units could handle even large transfers without difficulty. The versatility of the MP15DC meant that a single locomotive could handle multiple assignments in a single day. It might work a morning yard job, head out on a noon local freight, return in the afternoon for more yard work, and finish the day on a transfer run. This flexibility meant railroads could get maximum utilization from their MP15DCs, which improved the economics of ownership. The MP15AC, the technological advance. In 1975, just a year after introducing the MP15DC, EMD took the design in a new direction with the MP15AC. This variant addressed specific operational challenges that some railroads faced, particularly in hump yard operations and heavy industrial switching. The AC designation was somewhat misleading. It didn't mean AC traction motors, which wouldn't become standard until decades later. Instead, it referred to the electrical control system, which used alternating current in a novel way. The MP15AC used the same 12-645E engine as the MP15DC, producing the same 1,500 horsepower. The traction motors were still DC motors, but between the engine and the motors, the electrical system was completely different. Instead of an alternator producing AC power that was immediately rectified to DC, the MP15AC used a more sophisticated system. The engine drove a static inverter system that produced precise AC power, which was then converted to DC for the traction motors through silicon-controlled rectifiers. This sounds like unnecessary complexity, but it provided significant advantages in specific applications. The AC control system allowed much finer control of motor voltage and current, particularly at very low speeds. This meant smoother starts, better control when shoving cars at walking pace, and more precise speed maintenance during hump yard operations. For railroads that needed this level of control, the MP15AC was worth the additional complexity. Hump yards were the primary market for the MP15AC. In a hump yard, cars are pushed over a hump, an artificial hill, and allowed to roll by gravity into classification tracks. The speed at which cars roll is controlled by retarders, braking devices that squeeze the car wheels. But before cars reach the retarders, their speed is determined by how fast the locomotive pushes them up the hump. Too fast, and the retarders have to work harder. Too slow, and productivity suffers. The MP15AC's precise low-speed control made it ideal for this work. Southern Pacific was one of the largest buyers of MP15ACs, using them extensively in their major hump yards. Union Pacific, Milwaukee Road, and several other railroads also operated MP15ACs, typically assigning them to facilities where precise control was more important than raw pulling power. These locomotives worked incredibly hard, spending entire shifts pushing cuts up humps, backing down, coupling to the next cut, and repeating the process hundreds of times per day. The electrical system on the MP15AC was more complex than the MP15DC, which meant maintenance required slightly more expertise. The static inverter equipment was housed in electrical cabinets that were accessible for service, but troubleshooting required technicians who understood AC to DC conversion systems and silicon-controlled rectifiers. For major railroads with well-equipped shop facilities and trained electrical technicians, this wasn't a problem. For smaller operators, the MP15DC's simpler DC system might be more appropriate. Visually, the MP15AC was nearly identical to the MP15DC. The electrical differences were internal, visible only when cabinet doors were opened. This external similarity sometimes causes confusion among observers trying to identify which variant they're looking at, but the operational differences were significant to the railroads using them. The MP15T, the efficiency variant, the MP15, introduced in the 1980s, represented EMD's attempt to improve fuel efficiency in response to the energy crises of the 1970s. Rising fuel costs had railroads looking for ways to reduce operating expenses, and EMD's answer was turbocharging. But the MP15T's approach to turbocharging was unusual and tells an interesting story about engineering trade-offs. Rather than turbocharging the existing 12-cylinder 645E engine, EMD designed the MP15T around an 8-cylinder turbocharged 645 engine. The logic was that fewer cylinders running under higher load would be more fuel efficient than more cylinders running at lower loads. The turbocharger forced more air into the 8 cylinders, allowing them to burn more fuel and produce approximately the same 1,500 horsepower as the 12-cylinder non-turbocharged engine. In theory, this should have provided better fuel economy, and in steady-state operation, it did. An 8-cylinder engine has less internal friction than a 12-cylinder engine, and under sustained load, this translates to efficiency gains. But switcher service isn't steady-state operation. It's constant acceleration and deceleration, varying loads, lots of idling, and frequent throttle changes. In this kind of service, the fuel economy advantages were less clear. The MP15T found its market primarily with railroads that used their switchers for longer runs, where the efficiency gains could be realized. CSX and Seaboard System were among the operators of MP15Ts, using them for both yard work and light road service. The turbocharged 8-cylinder engine provided adequate power for these assignments, while theoretically offering better fuel economy on longer runs. However, the MP15T never achieved the production numbers of the MP15DC, or even the MP15AC. The added complexity of the turbocharger, one more component to maintain, one more potential failure point, offset some of the fuel economy benefits for many operators. The smaller number of cylinders also meant less redundancy. If one cylinder failed on a 12-cylinder engine, the locomotive still had 11 cylinders operating, but losing one cylinder on an 8-cylinder engine was more significant. The turbocharger itself required maintenance. Turbochargers operate at extremely high speeds and temperatures, and they need clean oil and proper operating procedures to achieve long service life. In switching service, with constant speed changes, turbochargers don't operate under ideal conditions. While EMD's turbochargers were robust and reliable, they added complexity that some operators preferred to avoid. Visually, the MP15T could be distinguished by its exhaust stack configuration and sometimes by external details related to the turbocharger installation. The sound was also different. The turbocharged 8-cylinder engine had a distinctive note compared to the naturally aspirated 12-cylinder engine of the MP15 DC. Applications across industries. Regardless of variant, MP15 family locomotives found work in an impressive variety of settings. These applications demonstrate just how versatile the multi-purpose concept proved to be. Ports on both coasts operated MP15s extensively. The Port of Los Angeles, Port of Long Beach, Port of Oakland, all used MP15s to handle the constant flow of container traffic. These locomotives worked around the clock, moving container cars between dock facilities and classification yards. The compact size allowed them to navigate the tight curves and limited clearances typical of port facilities, while the power was adequate for the loads they handled. Steel mills were major users of industrial MP15s. Integrated steel mills are enormous facilities with miles of internal track. Raw materials, iron ore, coal, limestone, arrive in hopper cars that must be spotted at the appropriate furnaces or storage areas. Finished steel products, coils, plates, structural shapes, are loaded into gondolas or flat cars for shipment. The MP15's reliability was critical in this environment, where furnaces operate continuously, and any disruption in material flow causes expensive problems. Refineries and chemical plants used MP15s to handle tank cars containing crude oil, finished petroleum products, and chemical feedstocks. Safety was paramount in these facilities, where even a minor accident could have catastrophic consequences. The MP15's straightforward controls and excellent visibility made it well suited for this careful, precise work. Grain elevators and agricultural facilities used MP15s during harvest season, when trainloads of grain cars needed to be spotted for loading or unloading. These assignments were seasonal and intense. During harvest, the locomotives might work around the clock to keep up with the flow of grain. During off-season, they handled lighter duties or were stored. Downtown terminal railroads, specialized carriers that operated in urban areas, switching cars between industries and connecting with multiple larger railroads, found the MP15 ideal. These operations required locomotives that could navigate street running, tight industrial sidings, and complex track arrangements while providing enough power for the loads handled. The MP15's compact size and Blomberg truck option made it perfect for this work. Military bases and defense installations operated MP15s for internal transportation needs. These facilities often had their own rail systems for moving ammunition, fuel, vehicles, and supplies. The MP15 provided reliable power for these operations, and its relatively simple maintenance requirements meant base personnel could keep them running without extensive specialized training. Universities with engineering or transportation programs sometimes acquired MP15s for training purposes. These locomotives provided hands-on learning opportunities for students studying diesel technology, railroad operations, or mechanical engineering. Several technical colleges and railroad training centers operated MP15s specifically for educational purposes. The variety of applications demonstrated that EMD had correctly identified a market need. The multi-purpose concept worked because real railroad operations needed exactly this kind of versatility. The MP15 wasn't too specialized for yard work, wasn't too limited for light road work, wasn't too complex for industrial operations, and wasn't too simple to handle sophisticated hump yard assignments. It was, as the name suggested, truly multi-purpose. In the 2000s and 2010s, new switcher designs arrived. Gensets, locomotives with multiple smaller engines that could be shut down individually to save fuel, were marketed as the future of yard power. EMD itself offered the SW1000R and SW1500R, rebuilt versions of older switchers. Progress Rail introduced ETO rebuilds with modern emissions controls. Battery electric switchers were tested. The technology was moving forward, but the MP15 didn't fade away. It was too reliable, too simple, too flexible, and too economical to replace. The economics of MP15 ownership were compelling. A locomotive built in the 1970s or 1980s, properly maintained, could still do everything it was originally designed to do. The mechanical systems didn't wear out if serviced correctly. The 645 engine could be overhauled repeatedly. Electrical components could be replaced. With systematic maintenance, an MP15 could work indefinitely. Compare that to the cost of a new locomotive, several $1 million, and the decision to keep running existing MP15s was obvious. This realization led to comprehensive rebuild programs. Rather than scrapping aging MP15s, railroads and locomotive leasing companies invested in bringing them up to like-new condition. Progress Rail developed rebuild packages that addressed every system. Engines were pulled, disassembled, inspected, and rebuilt with new or remanufactured components. Electrical systems were updated, sometimes with modern solid-state controls. Trucks were rebuilt, with new wheels, bearings, and brake components. Cabs were refurbished, with new seats, windows, and control stand components. The locomotives emerged from these rebuilds looking and performing like new units. Some rebuilds went further, converting MP15 ACs to MP15 DC configuration. The AC control system, while providing excellent performance, was more complex to maintain than the simpler DC system. As the original AC equipment aged and became harder to service, some operators chose to replace it with DC systems during rebuilds. This conversion simplified maintenance and made the locomotives more compatible with the rest of their fleets. Emissions upgrades became increasingly important as environmental regulations tightened. The original 645E engines met the emission standards of the 1970s and 1980s, but modern Tier 2 and Tier 3 standards required updates. Some rebuilds included installing modified fuel injection systems, updated turbochargers, and exhaust after-treatment systems to reduce emissions. These upgrades allowed MP15s to continue working in areas with strict air quality regulations, such as California ports and urban areas. Cab rebuilds improved crew comfort and safety. Original MP15 cabs were functional but Spartan. Rebuilds often included better seats, improved climate control, enhanced lighting, upgraded control stands, and modern safety equipment, like event recorders and positive train control interfaces. These improvements made the locomotives more pleasant to operate and brought them up to modern safety standards. Paint and appearance were part of many rebuilds. Fresh paint not only improved appearance, but also protected the car body from corrosion. Many rebuilt MP15s emerged in updated paint schemes, sometimes with modern corporate logos and branding. Some operators applied distinctive rebuild schemes that made it easy to identify which units had been through the program. Leasing companies became major owners of rebuilt MP15s. Companies like GATX, CIT Group, and others purchased MP15s from Class 1 railroads, rebuilt them, and leased them to short lines, regional railroads, and industrial operators. This created a vibrant secondary market for MP15s. A locomotive that had served its original owner for 30 years might get a comprehensive rebuild and start a second career with a completely different railroad. Short-line railroads embraced rebuilt MP15s enthusiastically. For a regional carrier operating 50 or 100 miles of track with modest traffic levels, a single rebuilt MP15 might be perfectly adequate power. The low maintenance requirements were particularly attractive to short lines with limited shop facilities. The ability to perform most routine maintenance with standard tools and generic diesel parts reduced operating costs. The MU capability meant that if a short line did need more power for a particularly heavy move, they could lease a second locomotive and run both units together. Industrial operators continued buying and operating MP15s. Steel mills, refineries, ports, and other facilities that had operated MP15s for decades found that well-maintained units could continue working for years. Some industrial operators purchased used MP15s from railroads, rebuilt them, and put them into service. The simplicity and reliability that made the MP15 attractive in the 1970s remained attractive in the 2020s. Major Class 1 railroads still operate MP15s in various roles. Union Pacific maintains a fleet for yard and local service. BNSF uses them in certain terminals. CSX operates several dozen. Canadian Pacific and Canadian National continue running MP15s, some of which have been in service for over 40 years. These locomotives typically work yard assignments, local freights, and industrial switching, exactly the roles they were designed for. International operators acquired used MP15s as well. Mexican railroads purchased units from U.S. operators and put them to work on their systems. South American operators imported MP15s for industrial and port service. Even some African operations acquired MP15s. The fundamental soundness of the design translated well to different operating conditions and maintenance practices. Museum preservation efforts have saved representative examples of the MP15 family. Railroad museums recognize the historical significance of these locomotives as the final evolution of the traditional American switcher. Several museums maintain operational MP15s, using them for excursions, demonstrations, and special events. Others have static MP15 displays, carefully preserved as examples of 1970s and 1980s locomotive technology. The aftermarket for MP15 parts and services remains robust. Remanufacturers supply rebuilt engines, traction motors, and electrical components. Suppliers stock filters, bearings, gaskets, and other wear items. Specialty shops offer painting, rebuilding, and upgrade services. This complete support infrastructure makes long-term MP15 operation practical and economical. What's remarkable is that the MP15's survival isn't driven by nostalgia or historical sentiment. These locomotives continue working because they're still the right tool for many jobs. They provide adequate power for switching and light road work. They're simple enough that most diesel mechanics can maintain them. They're reliable enough that railroads trust them with critical assignments. They're economical enough that operating them makes financial sense. That's the ultimate validation of EMD's design. The rebuild era has effectively extended the MP15's service life indefinitely. As long as frames remain structurally sound and major components can be rebuilt or replaced, these locomotives can continue working. Some units built in the 1970s have been through multiple rebuilds and are still in regular service. There's no reason they can't continue for decades more. This longevity proves what EMD understood when they designed the MP15. The best machines aren't the most powerful or the most technologically advanced. They're the ones that keep working year after year, doing their jobs without drama or excessive maintenance. The MP15 family has proven that principle beyond any doubt. These locomotives have been working for 50 years, and they're not done yet. The MP15 family represents the end of an era, the last generation of classic American switchers built to traditional design principles. After the MP15, switcher design would change dramatically, driven by environmental regulations, fuel economy concerns, and changing operational practices. But the MP15 captured something that subsequent designs haven't quite replicated: the perfect balance of power, simplicity, and versatility in a compact package. These locomotives were built for yards, but they were ready for road duty. They could work a classification yard all day, then head out on a local freight when needed. They could handle precise hump yard operations requiring delicate speed control, then pull transfer runs requiring sustained power. They could work in the brutal environment of a steel mill, then switch cars at a grain elevator. This flexibility, this genuine multi-purpose capability, was the MP15's defining characteristic. The simplicity of the design was its strength. A 12-cylinder diesel engine, DC traction motors, straightforward electrical controls, robust mechanical systems. There was nothing exotic about any of it, but every component was proven, reliable, and maintainable. When something broke, you could fix it. Parts were available. Procedures were documented. You didn't need a computer to diagnose problems or specialized tools to perform repairs. A competent diesel mechanic with standard equipment could keep an MP15 running almost indefinitely. That maintainability has proven crucial to the MP15's longevity, while more sophisticated locomotives have been retired. Because repairs became too complex or expensive, MP15s continue working because fixing them remains straightforward and economical. The long-term cost of ownership for an MP15 is remarkably low for a machine of its capability. This has kept them valuable in the secondary market and attractive to operators who need reliable power without the complexity of modern designs. The people who worked with MP15s developed deep appreciation for them. Engineers valued the straightforward controls and predictable behavior. Maintenance crews appreciated that the locomotives were designed to be worked on, with good access to components and logical system layouts. Operations personnel liked the flexibility. An MP15 could handle almost any assignment that didn't require high horsepower. That universal appreciation from everyone who dealt with these locomotives says more about their quality than any specifications could. The MP15 also represented EMD at the height of their locomotive building expertise. By the 1970s, EMD had been building diesel locomotives for 40 years. They understood what worked and what didn't. They knew how locomotives were actually used and maintained. All that accumulated knowledge went into the MP15, and it shows in every detail. This wasn't a revolutionary design or an experimental prototype. It was the culmination of decades of steady refinement, a locomotive that got all the details right, because the designers had learned from thousands of locomotives that came before. The sound of an MP15 is distinctive to anyone familiar with switchers. The steady beat of the 645 engine at idle, the rising growl as the throttle advances, the mechanical symphony of traction motors under load, these sounds have been the background noise of American rail yards for 50 years. They're as much a part of the railroad soundscape as the horn or the squeal of flanges on curves. And today, decades after the last MP15 was built, those sounds continue echoing in yards across the continent. Visually, the MP15 captured the essence of what a switcher should look like. The long hood containing the engine and electrical equipment, the compact cab with large windows for visibility, the trucks positioned for good weight distribution and traction, the whole package measuring just over 54 feet long, compact enough to maneuver in tight spaces, but substantial enough to handle serious work. The proportions were right in a way that makes the MP15 instantly recognizable, even to casual observers. The legacy of the MP15 extends beyond the locomotives themselves. The design philosophy, build it simple, make it reliable, ensure it can be maintained anywhere, influenced subsequent locomotive development, even as the specific designs changed. The idea that versatility and maintainability might be more valuable than raw power or technological sophistication wasn't new, but the MP15 demonstrated it so convincingly that the lesson couldn't be ignored. Today, their exhaust still echoes in rail yards across North America. From major classification yards on Class 1 railroads to small industrial sidings serving local businesses, MP15s continue doing what they were built to do. They sort cars, build trains, spot industries, and make the transfers that keep freight moving. They work alongside locomotives that are 40 years newer, with computer controls and AC traction and emission systems that didn't exist when the MP15 was designed. But the MP15 keeps working, proving that sometimes the old ways still work best. For small-town America, where a short-line railroad might be served by a single MP15 making the rounds twice a week, these locomotives have become part of the landscape. The sound of the horn announcing the train's arrival, the sight of the compact switcher shoving cars into the grain elevator or lumber yard, the friendly wave from the engineer leaning out the cab window. These have been constants for generations. The MP15 connects today's rail operations to a tradition stretching back through the SW series, through the NW series before that, through the early box cab switchers, all the way back to the beginning of diesel locomotives. It's the last link in a chain of development that spans a century. The fact that MP15s from the 1970s are still considered valuable, still worth rebuilding and modernizing, still economical to operate, this proves the fundamental soundness of the original design. EMD built these locomotives to last, but even they probably didn't imagine they'd still be working 50 years later. Yet here they are, rebuilt and repainted perhaps, modernized with current safety equipment, but fundamentally the same machines that rolled out of Lagrange in the 1970s and 1980s. The MP15 family taught the railroad industry lessons that remain relevant. Simplicity has value. Reliability matters more than peak performance. Maintainability determines long-term economics. Versatility provides options that specialized designs don't. These aren't revolutionary concepts, but the MP15 lived them so completely that the lessons became impossible to ignore. Every time a railroad chooses to rebuild an MP15 rather than buy new power, they're acknowledging these truths. In a world obsessed with the new and the technologically advanced, the MP15 stands as a quiet rebuke to planned obsolescence. These machines were built to work, and they're still working. They've outlasted locomotives that were supposed to replace them. They've survived changes in ownership, changes in operations, changes in technology. They've adapted to new emission standards, new safety requirements, new operating practices, and through it all, they've kept doing their job. The MP15 was the last classic American switcher. Nothing built since has quite captured the same balance of capability, simplicity, and practicality. And perhaps nothing will, because the priorities that drove the MP15's design, long-term reliability, straightforward maintenance, genuine versatility, aren't always the priorities that drive modern locomotive development. But the MP15 proved those priorities have value, and it's still out there proving it every day. Built for yards, but ready for anything. Simple enough to survive 50 years. Tough enough to work in every corner of North America. This was the MP15 family, the last great switcher, and a fitting end to a dynasty that began when diesel locomotives first rolled into American rail yards. The era of the classic switcher may be over, but as long as MP15s keep working, that era hasn't truly ended. It's just continuing, quietly, in yards and industrial sidings across the continent, where these compact locomotives go about their business exactly as they were designed to do. EMD MP15, 1974 to today. Still working strong,